Weak acids are those that don't dissociate completely when dissolved in water. Some common examples of weak acids are acetic acid, formic acid, trichloroacetic acid, hydrocyanic acid, hydrogen sulfide, water, hydrofluoric acid, and any conjugate acid of a weak base. For example, ammonia, NH3, is a weak base, and so its conjugate acid, which is NH4+, ammonium, is a weak acid. Let's say you had an example that asks you for the pH of a 3-molar solution of CH3COOH. The first thing to notice is that acetic acid is a weak acid. So when we put CH3COOH in water, so when it says a solution, we assume this is a solution in water, so an aqueous solution, it's going to form an equilibrium, which will make its conjugate base, which is just the same molecule but minus its acidic proton, so it's acidic H, and that proton is going to be transferred to the water, so it's going to make H3O+, or hydronium ion. I'm going to start out by drawing out a Rice table, so reaction, initial, change, and equilibrium. Now in this Rice table we can use either moles or final concentrations. Since there's no change in volume here, there's no change in concentration, so I can just plug in this concentration that's given in the question as my initial concentration. So I have 3.0 molar acetic acid. Now, I know only a little bit of it is going to dissociate in water because it's a weak acid, but I don't know how much. So I'm going to say that the change is minus X, where X is a small amount that dissociates. I start out with none of the conjugate base and essentially no H3O+, but any X that disappears on the left must appear on the right. So we can say plus X and plus X. So at equilibrium we have 3.0 minus X, and at equilibrium we have X, and we have X. In a question like this, you would also need to be told either the Ka or pKa of acetic acid. If we're told the pKa is equal to 4.75, the first step is that we'd need to convert that to a Ka. So pKa is equal to the negative log of Ka. So our Ka is equal to 10 to the negative pKa. In this case, our Ka is equal to 1.77 times 10 to the negative 5. Now we know the Ka is equal to the concentration of our conjugate base multiplied by the concentration of H3O+ divided by the concentration of our acid, so acetic acid. And remember, we leave water out of this. So this is just products over reactants. Now we know these concentrations. This is just equal to X, which I'm getting from here, multiplied by X, divided by 3.0 minus X. Now, because acetic acid is a weak acid, we assume that this X is very small. So we assume X is small, so 3.0 minus X is essentially equal to 3. We do this because it greatly simplifies the math. If we can't make this assumption, if this assumption would be invalid, we could still solve the question, but we'd need to use the quadratic formula. But by making this assumption, we can say now that 1.77 times 10 to the negative 5, so the Ka, is equal to X squared over 3.0. Now this is quite simple to solve. X is simply equal to the square root of 3.0 multiplied by 1.77 times 10 to the negative 5. So X is equal to 0.0073 molar. Now this, remember, this X is equal to our final concentration of H3O+, and what we're looking for is pH. So our pH is simply equal to the negative log of the concentration of H3O+, which is equal to the negative log of X. So this is just the negative log of 0.0073 molar, which is 2.14. So that's how you find out the pH of a weak acid.